Welcome to the Clear to Send podcast, a podcast about wireless engineering, where we educate you on Wi-Fi technology, talk about design tips, troubleshooting, interviews, and the tools. Here are your hosts, Roel and Francois.
Hello, good morning, everyone. Thank you for joining me here on a brand new episode of the Clear to Send podcast. Or good afternoon, good evening, wherever you are listening to this episode. I want to thank you for joining me here today again. And today I'm going to be doing this episode solo because Francois is actually traveling for work in a different country, and the time zones just don't quite work to our advantage where we both can be recording at the same time. I am down in Southern California in a hotel room because I was actually doing a Wi-Fi assessment for a warehouse. So I just wanted to record something really quick, something that I was doing a couple of days ago, where I wanted to look at dynamic bandwidth operation. And dynamic bandwidth operation has to do with how devices acquire the medium for larger channel widths like 40 megahertz, 80, and even 160 megahertz. But we have to maintain this backwards compatibility with older devices, right? Your 802.11a devices, because some of you guys still have those devices in your network. I know I see it. I see it here in this Wi-Fi assessment that I'm doing for this warehouse. So I wanted to talk about what dynamic bandwidth operation actually is, and whether or not I was able to capture this using Wireshark and then Ekahau Sidekick to try to really see how this works in a real world. So dynamic bandwidth operation is going to utilize RTS and CTS frames. From the beginning of 802.11, it was used to gain access to the medium and help with hidden nodes, and was understood by older devices as we moved into 802.11 AC. The RTS and CTS frames are transmitted at these lower data rates. Your RTS is your request to send, your CTS is your clear to send. When bonded channels came around, we started to think, okay, how would 802.11a devices understand that another device, maybe 802.11n or even 802.11ac, wanted to utilize a 40 megahertz, 80 or 160 megahertz channel width? Because 802.11a devices cannot understand the transmissions from those protocols, because they're these non-high throughput and very high throughput devices just won't understand those frames. So a few days ago, I tried to attempt this capture of the frame transactions between my Samsung S10 and my missed access point. I wanted to see if I could see this in action. So initially, when I started doing this, I was using one Sidekick and connected to my MacBook Pro. I was using Ekahau Capture to capture on an 80 megahertz channel width. I then had to resort to using two Sidekicks and a different laptop to capture each on a 40 megahertz channel width. And so I'll get into that as to why I had to make that change. So going back to how an 802.11a device would understand a very high throughput device wanting to utilize more than a 20 megahertz channel width, that's where the non-HT duplicate frame comes in. And that is, just as it sounds, it's a non-high throughput frame that is duplicated. Now, this frame is transmitted using in a method that is understood by all devices. So meaning an 802.11a frame. If my Samsung S10 wanted to transmit frames across an 80 megahertz channel, that RTS frame would have to be duplicated across 3 additional channels. So that allows any device operating on those channels to set their nav right from them hearing that RTS or CTS frame. So for example, if I'm using channel 36 at an 80 megahertz channel width and my primary channel is 36, then my device would transmit an RTS, but it would be duplicated on each of the 20 megahertz channels. So in addition to channel 36, it would duplicate that RTS on channel 40, 44, and 48. So 3 additional RTS frames. This is to indicate that the device would like to transmit using an 80 megahertz channel width. And that's the part that I wanted to capture, was these duplicated frames across each of these 4 channels, or the duplicate frames on 3 channels. In 802.11 AC, these duplicate frames are used for what's called bandwidth signaling. And the RTS and CTS frames work together to clear the channels that would be used for the device to transmit its data. And when I was reading about this, I tried to use both the 802.11 standard and also this. My primary context for understanding this was, can't even remember the name. It's a book by Matthew Gast. It's on 802.11 AC, and he writes about this pretty clearly, about 802.11 AC in general. And so then I started digging into just dynamic bandwidth operation, and I'll get to the dynamic part. So to see this in action, there is an individual or group bit in the transmitter address that is going to be set to 1, which would make that address a bandwidth signaling transmitter address. The AP, on the other hand, being the receiver of the RTS, would perform a clear channel assessment, or CCA, to determine whether or not those channels are clear to use, and it would transmit a CTS for the channels that are available, right? So this is where the dynamic portion comes into play of dynamic bandwidth operation. So if in an ideal scenario, a CTS for all 4 20 megahertz channels would be sent, but then the AP determines after CCA that only 2 of those 4 channels are free, then the AP would transmit a CTS frame on just 2 channels, allowing that device to access the medium using a 40 megahertz channel. So that's where that dynamic bandwidth operation comes into play. Is you have a device wanting to transmit and send data on an 80 megahertz channel, but the receiver of that RTS would perform CCA and determine, all right, hey, you can use 80 megahertz channel. Here's a CTS for all 4 channels that you requested, your RTS. And if it's not available, then it may drop it down to, say, 40 megahertz or even just a 20 megahertz channel. And so what does this really mean for us, right? So if we think about channel planning and also channel overlap, while you may be able to configure your Wi-Fi network for 80 megahertz wide channels, right? If you come into an environment, you see that they're using 80 megahertz all over the place. Those devices may not be able to acquire the full 80 megahertz channel width to transmit their data. And so this is where we run into situations where people do not have good performance, right? You have 80 megahertz channel widths configured, but you're wondering, why can I not get the throughput that I expect? And that's because through RTS and CTS, non-high throughput duplicate transmissions, a device will dynamically acquire the smaller channel widths, giving you less throughput than expected. Because if you've got some density of devices and you've got multiple access points, maybe even at 2 or 3 access points and more, then you're not going to be able to acquire the full megahertz, full 80 megahertz channel, because of the other devices transmitting and receiving data on the overlap of channels, right? Because right now we just don't have enough available channels to reuse an 80 megahertz wide channel. And in situations where you're in maybe a high rise, right, or you've got a lot of neighbors, then you'll see, even if you just use a Wi-Fi network scanner like Wi-Fi Explorer, you'll be able to see how many networks overlap on top of yours using an 80 megahertz channel width. And so that's what I was trying to capture, because I do have neighbors that are pretty close to me that are on the same channel as me. And going back to how I was trying to capture this, the reason why I had to use 2 sidekicks was when I first started doing the capture on my single sidekick, I had it set to an 80, capturing on 4 channels, but I wasn't seeing an RTS duplicated on each channel. And I was messaging Francois about this, and he gave me a tip to use 2 sidekicks. So I have a sidekick for myself. I have one at work. I drove into work and got my second sidekick and my work laptop. And I started capturing at the same time, but only capturing on 40 megahertz channels. And this is so I could try to capture everything in such a short time frame, because the RTS and CTS, the RTS frame is duplicated across all the channels for all 4 channels on 80 megahertz at the same time. And I just wasn't seeing 4 RTS frames, for example. And I don't know if my dwell time was set too short, or it just wasn't able to capture it. But I thought I captured it with 2 sidekicks. So what I did, I have 2 P caps from each sidekick. And Francois gave me the tip, hey, merge those 2 captures together in Wireshark. So when you open one P cap, and I'm using a Mac, if you go to File and then there's an option for merge, you can select the other P cap and merge them together into one file. So that's what I did. And using the timestamps, I was able to see what I think was the duplicate frames. But the one problem that I have trying to identify is this individual group bit that's set to 1. That part I cannot see. So I may need some of you guys to confirm with me that you are able to see this, and maybe I'll put my frame capture online for you guys to look at. But that's what I was trying to aim for. I wanted to capture it, and maybe I just didn't have the right setup. I was doing this relatively quick, but I did spend a lot of time just trying to capture this and see it for myself. And maybe I need to try a different access point, for example. But what I see in my capture, for example, I was on DFS channels, and this may affect it as well. But I could see on the primary channel the RTS, and then I see the same RTS being duplicated across 3 other channels with a lower data rate and also the same duration. And in response to those RTS frames, I see an individual CTS frame for each one. And that's where I really thought maybe I did get it, but I could not see the individual group bit set for the transmitter address in the RTS frame. And so that's what I need to check out. But that's what I wanted to look at and kind of analyze to understand dynamic bandwidth operation. And maybe if you're trying to do some analysis and figuring out why you're unable to see the throughput that you think you are supposed to receive over 80 megahertz channel widths or even 160 megahertz, maybe you need to dig into the frames over the air and see if your devices are even able to acquire the medium at each of those channels. And so you could see that with the RTS and the CTS. So that's my episode today. I wanted to keep it kind of short, give you something to think about, and maybe you can enlighten me on what you're able to find and what you're able to know with dynamic bandwidth operation and how it affects us as we move into 802.11ax, for example. So I hope you guys have a wonderful week. Let me know what you guys think of this episode. So I'll put this up on cleartosend.net, or you can hit us up on Twitter, and that's at cleartosend. So I hope you guys have a great time. I'm going to finish up my Wi-Fi assessment here in the warehouse, and maybe I can share what I was able to find there as well. Thank you guys for listening, and I'll see you on the next episode.